there are almost daily reports that black holes have been found. Has anybody actually found a black hole?
The answer to that is no. No one has ever found a black hole. There are two characteristics that are alleged for these black holes, and one is an event horizon and a singularity, and no one has ever found either one of them. And the other thing is that the true definition of black hole universe is that it contains only one mass, and that's the black hole itself. So you can't have multiple black holes. So consequently, no one can say that there are black holes all over the universe. And so they can't find any because there's nothing to find.
You say that there are different types of black hole universes and Big Bang universes, and they can't coexist. What does that mean?
Well, there are 4 different types of black holes that have been alleged in theory, and I can list them for you quickly. It's non-rotating charge neutral, non-rotating charged, rotating charge neutral, and rotating charged. So there are 4 types. Sizes don't matter. And then there are 3 types of Big Bangs. One is a spatially finite universe that's expanding, and the other 2 are spatially infinite universes of different characteristics, and they're expanding. And so, by their very definitions, they can't coexist because, let's take for example, black hole universes are all eternal, but all Big Bang universes are of a finite age. And so, similarly, black hole universes are spatially infinite, but we have the 3 Big Bang universes. One is finite and 2 are infinite in a different characteristic. So they can't coexist by definition. So when you hear a person talk about black holes and Big Bangs together, they never specify what type of Big Bang and what type of black hole. They always just say Big Bang, black hole. Well, this doesn't tell us anything. And the other thing is, as I pointed out, they can't coexist by their very definition, so it doesn't make any sense.
Scientists tell us that they have found a radiation relic of a Big Bang in a cosmic microwave background. Where does this radiation come from?
The idea of the scientists propose is that this Big Bang radiation in microwaves is a relic of the early stages of the universe from their Big Bang theory. And they carry out a number of experiments to detect this radiation. However, they've never proven that this radiation comes from space. The truth of the matter is, if you put a glass of water in a microwave oven and turn it on, what happens to the water? Anybody who's used a microwave oven knows that the water gets hot, and it does so by absorbing microwaves. So that means water is also an emitter of microwaves. Well, when we consider this very simple truth, we know that the surface of the Earth is mostly 70% covered 70% by water, and there's water in the atmosphere all the time. And in steady state conditions, we have microwave radiation throughout the atmosphere. And the most distant detection of the microwave, so-called microwave background, of the mean temperature of the universe that they tell us, has been at an altitude of 900 kilometers with a satellite that could not protect itself from microwaves. So the truth is that the microwave detection for the temperature of the universe is actually microwave signals from water on Earth. It does not come from the cosmos.
Okay, thanks for the interview.
Thank you very much. I'd like to first begin by dedicating this to my brother, Paul Crothers, who died in 2008. And the first thing I'd like to point out to you is that you might not be aware of it, but there are more than one type of black hole. When you hear a proponent of black holes and Big Bangs talk about them, do they ever tell you what kind of black hole and in what kind of Big Bang universe? Never. They seem to be even unaware of it themselves, that they have 4 types of black holes and 3 types of Big Bang universes. Let's run through them very quickly. We have non-rotating charged neutral, so-called Schwarzschild black holes. Then we have non-rotating but charged black holes. These are called Reisner and Nordstrom black holes. Then we have rotating charge neutral. This is a Kerr black hole. And finally, rotating charged black holes. This is a Kerr-Newman black hole. But with Big Bangs, we have 3 different types. And it all depends on this strange thing here called K. It's called a curvature, a constant curvature. That's what we'll say about it. And it tells you which one is which. Well, if we have K equals -1, we have a negatively curved space-time. It's spatially infinite and expanding. If we have K equals 0, we have a flat space-time, which is spatially infinite and expanding. Now we have K equals 1. This is positively curved space-time. It's spatially finite, expanding, and later contracting. So I pose to you again, when a proponent of black holes and big bangs says anything about this, do they ever tell you which one they're combining with which? Never. Why? They don't seem to know. But without specifying what black hole in what big bang universe, they're not telling you much. Right? So let's have a look at what they actually do here. But before so, the first thing is, let's compare all types of black holes, the 4 types. Now I'll point out quickly that the sizes of black holes don't matter. We're all certain types of human beings. There are races of man. I'm a Caucasian. Probably most of you are. Some of you might not be. But that's a type of human being. But small or big, I'm small. But I'm still a Caucasian human being. Well, black holes, size-wise doesn't matter either. They say that there are micro black holes, mini black holes, intermediate black holes, supermassive black holes, ultra supermassive black holes, and now they're telling us we have obese black holes. I don't know where they're going to stop. They don't seem to stop. They just keep adding adjectives, and that makes bigger and bigger black holes. But the fact of the matter is they're all only of these 4 types. Now let's compare the black holes to big bangs. All types of black hole universes are spatially infinite. We go to the big bangs. Well, one of them is spatially finite, and the other 2 are spatially infinite, and there are 2 different types of infinity. Do they match? No. Let's have a look at this one. All black hole universes are eternal. Technical terms are static or stationary, but they're eternal. Well, every one of the big bangs, rather, that are alleged are of a finite age. How old? Well, they tell us maybe it's about 13.8 billion years. But does that match? No. Black hole universes, well, they actually only contain one mass. I'll talk about that a bit later. And we can compare it with big bangs. They're supposed to contain radiation and many masses, including black holes. But that doesn't match. No black hole universe is expanding. All black hole universes are not expanding. But all big bang universes are expanding, except the finite one. That might contract. We don't know when, but maybe. And finally, this is a little bit of a technical term, all black hole universes are asymptotically flat, or asymptotically fat, they could be, asymptotically flat, or asymptotically curved. And all big bang universes are not asymptotically anything. So does that match? No. Well, we've got 5 mismatches here, and these are all generic characteristics of these different universes. And I'll point out also, we saw in the last slide, a K curvature. Well, notice that no black hole universe possesses a Big Bang constant K curvature. That's another big difference. Well, that's what defines the 3 different Big Bangs. It's got nothing to do with black holes. So we see that these universes are mutually exclusive. How do they then put together a black hole universe? It's infinite, spatially infinite, and it's eternal, and they stick it into what? Maybe a finite one that's of a finite age. Finite in size, finite in age. It can't possibly match. Whether they stick that into one of their infinite ones. Well, the 2 infinite ones of Big Bangs don't match the infinity of the black hole. They're different because this one doesn't have a K curvature. And it's still eternal. They're Big Bangs that are expanding. They're still a finite age. How much? Still, we're around about 13.8 billion years. They've edged it up from 13.65, and over the years it's got up to 13.7, 13.72, 13.75. Now it's 13.8. They're tweaking all their little bits and pieces. But you see, none of these match. So when anybody says to you, I've got all these black holes floating around in the universe and it's expanding, what are they talking about? Nonsense. Their very definitions, which they forget, exclude this. It's not possible. The theory doesn't allow it. Now, if you don't know which Big Bang you're going to talk about, let's talk about the whole lot at once.
That's what they do. Look, now Lineweaver and Davis wrote an article for the Scientific American. They say this: the idea that the Big Bang was small is misleading. The totality of space could be infinite. So which Big Bang are they talking about? The infinite ones? There are two of them, and they're different. And the finite one? Well, it could be, because the totality could be finite, could be infinite. That means it could be finite. They're giving you three at once. This is not science. This is what we call double talk. Now we come here. Weinberg. Weinberg's at the University of Texas at Austin. He's a Nobel laureate. He says all space in this context may either mean either an infinite universe or all of a finite universe. So he's giving you three Big Bangs at once. Well, you can't have three Big Bang universes at once. Which one do you want? You only live in one universe. Unless, of course, you're Larry Krauss, you have multiple universes called a multiverse. And the Big Bang happened everywhere. In the room in which you are reading this article, in a spot just to the left of Alpha Centauri, everywhere. But the space between the galaxies and us is expanding. Now notice this. Where is a spot next to Alpha Centauri? A spot is pretty small. Bill Gates talked about spots. And where's Alpha Centauri? Well, it's smack bang inside, yes, the galaxy that we live in. But the space between the galaxies and us is expanding. So the Big Bang happened everywhere, but only the space between the galaxies is expanding. The spot next to Alpha Centauri, they're not separating from each other. Why? The Big Bang happened there too, didn't it? Yes, it happened here on my desk. Happened everywhere. But for some reason, we're not allowed to have the space next to the spot, or the spot next to Alpha Centauri expanding. Nothing else is expanding except the space between the galaxies. So they give you a balloon, they blow up a balloon, they put spots all over it and say, look, the balloon is blowing up and the spots are moving apart. But the spots themselves, they don't change their size. Really? If you put spots on a balloon and blow it up, do the spots expand? Yeah, obviously. No, not according to a cosmologist. The galaxies don't expand. Only the space between them. Although their Big Bang happened everywhere, including the spot next to Alpha Centauri in our galaxy. Here is a technical reason why you can't add Big Bangs and black holes. We've already seen you can't because their definitions preclude it. Here's a little bit of mathematical mumbo-jumbo that they violate. General relativity is what's called a nonlinear theory. And this means that the principle of superposition doesn't hold. What does that mean? Well, it means if I've got one mass and I take another mass somewhere and I'm going to stick it together in the universe, I've superposed those masses now together in the universe. I can put in more and more, can I? Well, if you're talking about Newton's universe, you can. Newton doesn't put any limitation on how many masses you can have. And when you look in the sky, you have to have a theory that will allow you to put all those masses in, because there are lots of masses out there. Right? But can you do it with general relativity? No. It's a nonlinear theory. So let's take a specific example. Let X be some black hole universe and Y some Big Bang universe. And let Z be some other black hole universe. Remember, there are 4 types of black hole universes and they're all mutually exclusive. You can't put 2 of them together. Let's have a look at this. X plus Y is not a universe. Why? Because it's a nonlinear system. This is a linear combination. X plus Z is not a universe. So we've got a black hole and a Big Bang. You can't put them together. The theory says you can't. Well, we've seen you can't because the definitions don't allow it either. Well, X plus Y plus Z is not a universe either. They're superposing. But you can't superpose in general relativity because the theory is nonlinear. So the superposition is not allowed. Nonetheless, proponents of black holes and Big Bangs, they take some Big Bang universe, they never tell you which one. Then they take some black holes, and lots of them, and they never tell you which type. Then they superpose the whole lot together in violation of the very structure of the theory that they're using and the very definitions of holes and bangs, and tell you we've got lots of black holes in some non-specific Big Bang universe. Well, this is Tolman. He wrote a book long ago on general relativity, and he tells us this. Well, you'll see that Big Bangs are actually one-mass universes. So you can't even have multiple masses. We can then treat the universe as filled with a continuous distribution of fluid of proper macroscopic density and pressure, and shall feel justified in making this implication since our interest lies in obtaining a general framework for the behaviour of the universe as a whole, on which details of local occurrences could later be superposed. So Tolman's telling us that we can superpose all these things. You can't. The very theory that he's using prevents it. In general relativity, superposition is forbidden. You can't do that. In other words, when I gave you the example of X and Y universes, a black hole and a Big Bang, those two universes pertain to completely separate Einstein field equations, and they have absolutely nothing to do with one another. Why? Because they're very different equations. So you take a solution X for the black hole universe, and you take a solution Y for a Big Bang universe, completely different equations, and then stick them together, maybe with glue. But it doesn't work. It's a nonsense concept because it violates the very theory that they're using. Here's an interesting little argument. Einstein says his principle of equivalence is very important to general relativity. He tells us, I've shortened it because it's very long. All we need to know is this. Let now K be an inertial system. Masses which are sufficiently far from each other and from other bodies are then, with respect to K, free from acceleration. We shall also refer to these masses to a system of coordinates K prime, uniformly accelerated with respect to K. Notice that he's talking about lots of masses. And he says another way of saying this is that in any sufficiently small region of his space-time, and they can be anywhere, those regions, the laws of special relativity must hold. So we see from both of these 2 points here that each one of them requires the a priori presence of multiple, arbitrarily large, finite masses and some photons to be able to see anything. But where do they come from? All the black hole universes and the Big Bang universe violate this principle. Why? Well, we just saw that the Big Bang universe is a one-mass universe because it's continuous, homogeneous, can't be divided out. You treat it as though it's wholly full or completely filled by a continuous distribution of matter. It doesn't break up because as soon as you break it up, you've got multiple masses and you have no expressions for that. So black hole universes and Big Bang universes violate the very principle of equivalence that Einstein lays down as a basis for his theory. So that doesn't work. Let's consider forces, gravitational forces. If you put two balls, solid balls on a strings and hang them from the roof and you hold them still and then you let them go, what happens? Well, we know from the laboratory that they approach one another somehow. Cavendish did experiments like this. He found, yes, they go together somehow. But we find that in general relativity, in Einstein's new theory, gravitation is of a much more fundamental nature. It becomes almost a property of space. Gravitation is thus, properly speaking, not a force in the new theory. This came from Willem de Sitter, a Dutch astronomer who was a contemporary of Einstein. Well, that's true, because in general relativity, gravity is not a force. It's what? The curvature of space-time. So what's happening here is the curvature of the space-time here somehow pulling the curvature of the space-time here so that these two things go together, because we know that that happens in the lab, right? And it's not a force, mind you. When we look at it in the lab, it seems to be some kind of force. But in Einstein's theory, it's not a force, right? So this has no explanation in general relativity. In fact, general relativity can't even account for the presence of two masses, and it can't even account for the experimental fact that those two masses will approach one another if you release them. You hold them still, then release them, they come together. General relativity cannot even describe it, let alone explain it. And yet, we have general relativity being used to talk about black holes all over the place, in an expanding Big Bang universe, and it can't even deal with two masses. This is not a NASA photograph. I know that because it's an artist's impression. I know the artist. It's me. I drew this. You can tell I can't draw. This little astronaut, well, let's have what Hawking tells us. This is called spaghettification. You take a person and you stretch them like this and you turn yourself into a piece of spaghetti. Well, Hawking tells us gravity gets weaker the farther you are from the star. So the gravitational force, yeah, he's invoking forces again. Where did he get those forces from? It's not Einstein. There is no force in gravity in Einstein. This comes from Newton. So now he's mixing Newton's theory with general relativity, by invoking the forces. There are no forces in general relativity. And our intrepid astronaut's feet would always be greater than the force on his head. Well, when you look at my little drawing here, is he falling head first or feet first? He could be falling head first. That means this black hole or star might be above his head. Well, he's talking about feet, so we'll put it down here. So he is falling feet first. But you can't tell from the diagram. This is very interesting because every time you see a presentation of black holes and big bangs, they put up little diagrams like this sort of thing, and they put all this sort of double or vague talk in here, and you think, oh, he's falling. Yeah, but which way? We have to be sure. This is a technique that advertising executives often use to sell you things. Put up diagrams and drawings and things, and you get a sort of a subliminal effect. And so since there are no gravitational forces in general relativity, there's no weight. You go to the shop and you buy yourself some apples, right? Remember the old days? I remember the old days because I'm old. Because you used to go to the grocery store and you would have a dish hanging on a spring balance, and you put your apples in there, and the apples would be pulled down on the spring balance. The spring balance stretches, and the indicator goes like that and says, "Oh, you owe me €5." I don't know. You didn't have euros back then, whatever it was, right? So you paid for your apples. You take the apples out, and the spring balance pulls it back up. The spring balance exerts a force against the thing that's pulling it down. We're talking about forces. Can general relativity do that? No, can't explain it. Has absolutely no way of even describing it. So what's happening in our spring balance and our apples is the curvature of space-time of the spring balance somehow causing the curvature of the space-time of the apples to interact somehow to make the spring stretch so that the indicator works, and you can know how much to pay for your apples. It can't do it. So we see that it's all done by invoking Newtonian forces in a clandestine way. You're talking about general relativity, and then you talk about forces of gravity. That's a violation of logical thinking. Here's a little diagram of a black hole to explain to you why it is that a black hole is an infinite universe. It contains only one mass. If there is a mass, we're assuming that there is a mass, the black hole. We'll see later that there is none. But let's assume that there is one. Here's flat or curved space-time. So we see what we mean by asymptotic. You remember this from school. An asymptotic curve. It gets closer and closer. Does it ever touch? Never. Is there any limitation on how far this goes out? No. The word asymptotic means there is no bound. So if you don't have some sort of asymptotic feature here, right, then you don't have a black hole universe because we saw that they're defined as being asymptotically flat or asymptotically curved. So here it is. This goes to infinite curvature. That's an infinite gravity according to Einstein because gravity is space-time curvature. So here, infinite means the gravity must get infinite. Where? At a point. Maybe. I'll see later. We'll see later. It could be something else. So here may be a point. It's asymptotically flat. Yes, all right. As you increase the radial distance away from your singularity, you go asymptotically. Okay, that's good. We've got a pictorial idea of what it is now. We see there's no boundary here. So this describes this illustrates what they're talking about. Let's think of two of them to start with, just two. We put the two together. Here he is to the singularity of a black hole. It doesn't matter what type. I haven't specified what type of black hole here because it pertains to all of them. And this goes to another singularity, infinite curvature again. Well, let's look at black hole number 1. Is that asymptotically flat there? No. Is it asymptotically curved in here? No. And if you go away from this black hole and you encounter this black hole and you come to another, infinite curvature. Infinite curvature is a long way from being asymptotically flat or asymptotically curved. Now let's look at number 2. Well, is this asymptotically flat? No. Is it asymptotically curved? No. And this number 2 encounters an infinite curvature at black hole number 1. So neither of these can be asymptotically anything. Well, we've already seen that the definition of a black hole is asymptotically flat or asymptotically curved. So if you've got two of them, is it possible to have a black hole? No. Is it possible to have two of them together? No. Because this violates the very definition of what the black hole is. So how do they put all these black holes together? Well, according to Daniel Stern, he must be right. He's a NASA scientist. He tells us we've got the black holes cornered. Really? He says, well, they reckon that they found 2.5 million black holes with the NASA WISE survey. So he's got them cornered, all these 2.5 million of them. Well, let's look at this one, lots of black holes. I can't put 2.5 million in there, my box is not big enough. So we'll think about the 2.5 million. Well, let's think of one of them. Here it is, one of them. Each one of these 2.5 million black holes encounters 4,499,999 infinite curvatures all around it. Is that asymptotically flat? Is it asymptotically curved? Not a chance. So this is what? Complete and utter nonsense. Here's another gem. I love this one. I think you'll like it too when I explain it to you. Black hole escape velocity. No proponent of black holes even understands escape velocity. Yeah, they have no idea. Right? Escape velocity is a very simple concept. They don't understand it. Let's think of this. This might be the sun or the earth, say. If you have an escape, if you project an object, maybe a ball or a rocket, with the speed of the escape velocity or escape speed, this thing will get away and it doesn't fall down. But what if you throw a ball up into the air? What do? You throw it up into the air, the ball goes up, and it falls down. Why? Because its speed wasn't fast enough. It didn't have the escape speed. Did this leave the Earth? Certainly. Did this one leave the Earth? Well, it escaped, so it certainly left. This one didn't escape, but it certainly left. It went out, it got to a point where it stopped, and it fell back down. We know that every day. According to history, Newton was sitting under a tree, and an apple hit him on the head because it fell straight down. Now, let's consider a black hole. We have an event horizon. What do they tell you about an event horizon? They tell you that the escape speed is at the velocity at the event horizon is the speed of light, or maybe even greater than the speed of light. They tell you that the black hole, things go into the black hole, but nothing can come out at all. Well, here, things come out. Yeah? Here, nothing can come out. You go in, when you're in, you can't come out. You can throw a ball here, it won't get there. Nothing can even leave the event horizon. And there are no other bodies present. So what escapes from what? If you've got a one-mass universe, as we've seen with a black hole, how can you get the other mass to be even present to escape from it? You can't. And here, even if there was one, can it escape? If it goes in here, you're in here, can it escape? No, because here, at the event horizon, the speed of light is the escape speed. They say nothing can escape. That's the escape velocity of a black hole. Really? Can anything leave here? No. Did anything leave here? Yes. So this idea here that nothing can even leave violates the concept of escape velocity. Just because you have an escape velocity doesn't mean things can't leave. It means things can leave and fall down, or they can escape depending on their speed when they're at first projected. But here, there is no such thing as escape velocity. But they tell us nonetheless that the black hole has an escape velocity, and at the event horizon it's c, the speed of light. Not only that, this is what we find in the dictionary of geophysics, etc. Black hole, a region of space-time from which the escape speed exceeds the velocity of light. They're telling us it's got an escape velocity. We just saw it can't have one, but they're telling us it has one. Here's Hawking. I had already discussed with Roger Penrose the idea of defining a black hole as a set of events from which it is not possible to escape to a large distance. He's talking about escape again. It means that the boundary of the black hole, the event horizon, is formed by rays of light that just fail to get away from the black hole. Instead, they stay forever hovering on the edge of the black hole. What? They stay forever hovering on the edge of the black hole, but the escape speed of the black hole is allegedly what? The speed of light. Well, this is amplified by Professor Joss Bland Hawthorne of the Sydney University. He's at the Institute for Astronomy. He's an astrophysicist. He got on television, Australian national television. He said this. I really like this one. A black hole is a massive object, and it's something which is so massive that light can't even escape. Now, he's talking about escape again. There is no escape velocity. Some objects are so massive that the escape speed is basically the speed of light. Yeah, a black hole. And therefore, not even light escapes. So black holes are themselves are basically inert, massive, and nothing escapes. Let's have a look at this. He says it's basically the speed of light, and therefore not even light escapes. Well, the speed of light travels at what? The speed of light. He tells us that the escape speed is The speed of light. Then he tells us that even though light is travelling at the speed of light and therefore the escape speed, light can't escape. I wrote to him and I said, can you explain this, what you just said on national television? You know what he said to me? Stop sending me emails. That's his solution to this complete and utter nonsense. Right? But people don't realise what they're being told on television or in books or papers. I like this. This is really nice. Meisner, Thorne and Wheeler, they've had a mention today in some ways. Meisner, Thorne and Wheeler wrote a book on gravitation. It's the size of a telephone book. You can use it as a paperweight or a doorstop, right? But he says here, or they say, one crucial assumption underlies the standard hot Big Bang model, that the universe began in a state of rapid expansion from a very nearly homogeneous isotropic condition of infinite or near infinite density and pressure. Now I ask you, how close to infinite do you have to get to be near infinite? Really? Is it infinity minus 1? Maybe it's infinity plus 1, or infinity minus a billion. This is nonsense. You can't get near infinity, near infinite. Well, not to be outdone, Larry Krauss, the famous Larry Krauss who gets on television all the time, tells everybody everything about Big Bangs, ridicules lots of other people. He tells us, but this is what he did on 18th of February in 2013, last year, on Australian national television again, on a show called Q&A. You can get the transcripts, so you can get it and read it for yourself. But he says this, but it is that, in fact, because of discovering that empty space has energy, it seems quite plausible that our universe may be just one universe in what could be almost an infinite number of universes. And in every universe, the laws of physics are different, and they come into existence when the universe comes into existence. Well, how close to infinity did Larry count to get almost an infinite number? You tell me. Can you count to almost an infinite number? Not a chance. But he's telling television land, all the people in Australia at least, on national television, that he reckons you can get an almost infinite number. They do a lot of magic with these infinities. Here's another one. The work that Roger Penrose and I, this is Hawking speaking, the work that Roger Penrose and I did between 1965 and 1970 showed that according to general relativity, there must be a singularity of infinite density within the black hole. Well, now we come to the question of the singularities. There are two types alleged. One is a point. A point has 0 dimensions. It's a mathematical thing. The other black hole, it's for rotating. So we've got 4 types of black holes. 2 of them are non-rotating, 2 of them are rotating. So we have only 2 types of singularities. A point and the circumference of a circle. I'm not saying a circle. A circle has area. This is the circumference of a circle only. Now you tell me how you get mass into a point or into the circumference of a circle. You cannot. So what do? They say, well, the singularity is volume. That's 0. And we got the mass of the black hole. That's some mass m. Yeah? And we divide by 0 and we get infinity. They do that. They say, you can divide by 0. Well, you know you can't divide by 0. Every schoolboy knows that. Every schoolgirl knows that. And they get infinity. Well, when did infinity become a number? You can't do algebra with it. You can't do arithmetic with it. But they tell us that you get infinity to get an infinite density. So they divide by 0, get infinity, and assign physical properties to it. Well, that's their singularity of their black hole. Now, do they divide by 0? Yes, they do. Because this is from a book on astrophysics by Carolyn Ostley. A non-rotating black hole has a particularly simple structure. At the center is a singularity, a point of 0 volume. Yeah, we divided by 0 according to their rules. And infinite density, where all the black hole's mass is located. Space-time is infinitely curved at the singularity. The black hole singularity is a real physical entity. It is not a mathematical artifact. So they're dividing by 0. Here again, this is from Dodson and Poston, a book on tensor geometry. Once a body of mass, of any mass, of matter, of any mass m lies inside its Schwarzschild radius. That's the event, the so-called radius of the event horizon. It undergoes gravitational collapse and the singularity becomes physical, not a limiting fiction. So it's not elementary calculus where you take a limit. No, you actually divide by 0. Well, that's nonsense. Here is the universe comes from nothing. Hawking tells us at the Big Bang itself, the universe is thought to have had 0 size and to have been infinitely hot. Let's think about that. It's 0 size, but it has infinite hotness. What is there to have infinite hotness? And what is temperature? According to physicists, temperature is all these particles jiggling around. And the more they jiggle, the hotter it is. You put more energy, whatever that is, into it, and it jiggles and jiggles more. This is hotter. Well, if you've got zero size, how do you have space for particles? And where do they jiggle? And if it's infinitely hot, how fast are they jiggling? I don't think Hawking's thinking very clearly when he says this. Here, zero size and infinite hotness. This is a meaningless statement. This is Larry Krauss again, 18th of February 2013, on the same television show. He tells us that there's no real particles, but it actually has properties. But the point is that you can go much further and say there's no space, no time, no universe, and not even any fundamental laws, and it could all spontaneously arise. And it seems to me, if you have no laws, no space, no time, no particles, no radiation, it is a pretty good approximation of nothing. He's telling us that nothing is an approximation, a good one, of nothing. In other words, zero is a good approximation of zero, really. But it all came from nothing, mind you. That's zero. Oh, here's another good one. Again from Larry. He tells us, but I would argue that nothing is a physical quantity. It's the absence of something. I remarked in Albuquerque 2 weeks ago when I gave a talk there, I wondered, does this include the absence of neurons? You know, these are the bits in your brain. He got on television a second time. This is the 27th of May. He loves getting on television and telling his stories. There was nothing there. There was absolutely no space, no time, no matter, no radiation. Space and time themselves popped into existence, which is one of the reasons why it's hard. Someone stopped him talking there, see his little dots. You can see that in the transcript. Someone interjected. But with all of this, and they tell us dark energy, we need dark energy to make the universe expand. Hey, but Hawking tells us in his book, energy cannot be created out of nothing. They've just told us everything came from nothing. But he says, oh, but you can't create energy out of nothing. And they're dark energy. Isn't that energy? Yeah. Well, you can't create that out of nothing, according to Hawking, but they do. Now they talk about numerical methods. They have these magical numerical methods. You can't solve Einstein's field equation for two masses. You can't even write a set of field equations for two masses, let alone more than two. So they say, we'll use numerical methods. And they give you, well, binary black holes. Well, where do they get the binary black holes from? They superposed one black hole into another one. We see you can't do that. Then they say, let's apply numerical methods to these two things we just superposed, that you can't superpose, and we'll get some stuff out of that, and says, we can now find out lots of things about the universe by numerical methods on the two things that we just stuck together that you can't do. So numerical methods on nonsense produces what? More nonsense. Now I'm come to a little bit of technicality here, so please bear with me. These are ugly customers, I know. This is Einstein's field equations. This thing here, let's identify them so that everybody knows what it is and doesn't get confused or afraid. Because it's really simple. This looks really tough, complicated. It's really simple. This thing here is Einstein's tensor, the Einstein tensor. That's its name. We don't have to know what a tensor is. Don't worry about it. This thing here altogether, this is the cosmological constant. And they talk a lot about the cosmological constant. Yeah, we've included it here. And this thing here, this T, this K is just a constant. It's nothing. You know, y equals 5x. 5's a constant. K is just some constant like that. T is energy momentum tensor. Now we've named the bits. This equation, Einstein's field equation, is no longer confusing. We have a word expression for it now. So we can reduce this, or now that we've identified the parts, let's reduce it to what it means. Space-time curvature, yeah, that's his alleged gravitational field, is matched to the material sources. Why? Because he still has to have mass, or matter, to cause the gravitational field. Otherwise, if you don't have mass and matter, you don't have any gravity. So he says his field equations couple his gravitational field to its sources. Yeah, there it is. Here's the gravitational field with the cosmological constant, and it's coupled to its sources. There's the name of the bits. That's what it does. According to Einstein, everything except his gravitational field is matter. Yeah, radiation, charges, mass, electromagnetic fields. All of this is matter, according to Einstein. So, okay, matter then induces the space-time curvature. He still has to have a cause of his gravity, so that's it. Let's have a look at them. There's the co-equations again, just to remind us of the bits and pieces. And let's compare. He says, well, if you set the cosmological constant to 0 and you set the energy momentum tensor, that's the sources. You take out the sources from the equations, make them 0. His G That's naught. So this becomes G equals naught. But this G thing reduces to even something more simple called the Ricci tensor. So the Einstein tensor becomes a Ricci tensor. Note, but I put it in red, energy momentum tensor equals 0. But he tells us that this describes the gravitational field outside a body. He took them out with this hand, mathematically, and then he puts the mass back in with the other hand by saying outside a body. So this is a circular argument. Well, here it is, energy momentum tensor. This produces the Schwarzschild solution for a star or a black hole. Now let's go over to this side. T equals 0, material sources are gone again. The lambda, it's not 0, and we get this equation, because that reduces to this, and this thing stays there and it arranges so it comes out like this. Ricci tensor equals a cosmological constant term. Notice again that the energy momentum tensor is 0. Yeah, T's naught. There are no material sources. This one is called de Sitter's empty universe. Why? Because it contains nothing. There's no matter whatsoever. So we see here that according to Einstein, momentum tensor equals 0. That means material sources are both present and absent when energy momentum tensor equals naught. The very same mathematical constraint gives matter and a one mass universe and an empty universe. Well, that's not possible. You can't possibly do that. So what's this mean? It means this equation is nonsense. It means this equation is nonsense. Do you have a universe with nothing in it? Look into the sky. Yeah? See this one here? This doesn't mean anything. This contains nothing. This contains nothing. So as I said before, even their black hole solutions don't even contain a mass. It contains nothing. That concludes my little talk on black holes and big bangs.